Welcome everybody. Today it's a pleasure to have our own Mikhail Medvedev to give a seminar. He did his PhD at UC San Diego, and then he was a postdoctoral fellow at ITC, at Harvard, and at CETA. And after which he moved to University of Kansas as a faculty, where he is currently, and is visiting us for this sabbatical year. He's an expert in many areas of high energy astrophysics, but today we'll talk about prospects of X-ray imaging of the outer heliosphere and other atmospheres.
Yeah. Thank you very much for this introduction. Indeed, it was a little bit hard for me to decide which talk to give because I have several exciting projects, including vacuity plasmas and some others, dark matter in particular. But I think this one is very interesting. I'm actually very much excited about this project. It's a pilot project. It's not a full-blown project yet, but I think in general, just as a foreword, I think this what I'm going to talk about, this technique and the ideas are actually underappreciated in the community. And it's not hard to incorporate them in numerical codes that are available. So I actually encourage you to listen and probably jump onto that because it's a low-hanging fruit. So I'll be talking about the X-ray imaging of the heliosphere, and we'll tell just a couple of words about the astrospheres. So heliospheres about other helioses, so to say. And that's partly because we don't know much about that. So since it's a heliosphere, it's a bubble created by the solar wind. The solar wind emanates from the surface of the sun, and then it gets heated up and accelerated. It gets accelerated to produce the solar wind, which propagates through space at high velocity. We actually disentangle the two regions here near the equatorial region and the two polar regions. The speed here is drastically different. The speed of the solar wind is drastically different because over here we do have field lines, magnetic field lines, dipolar. Basically, one step back. The sun has magnetic field, and magnetic field is largely dipolar, what you see actually over here. The color here shows the direction of the interplanetary magnetic field. So it's inward here and outward here. So it's consistent with the magnetic field being dipolar. And the region near the equator, between plus and minus roughly 30 degrees latitude, is where you have closed field lines. And the closed field lines don't let the plasma propagate quickly away from the sun. So there is magnetic tension, and therefore the speed here is roughly 350 kilometers per second. Over here in the polar region here and here, you actually have open field lines, and plasma can flow freely along open field lines. So here we have speeds of about 700 kilometers per second, which exceeds actually the escape velocity from the sun, which is 618 kilometers per second.
So this is close to the sun. How far is it from?
Good question. This is the data taken by the Ulysses spacecraft in the 90s. So what's been done, the satellite's been launched from Earth in the galactic plane. And it went to Jupiter, made a gravitational maneuver to go out of the elliptic plane almost vertically, and went over the poles, both poles over the sun. So you can see it's actually a collection of data. Some of them are extrapolated toward the sun from the Jupiter distance or anywhere in between. So it's really a processed image. It's not, processed data. It's not really a snapshot at a given location. Actually, this travel takes some time. So they actually covered a little bit of minimum and a little bit of maximum. That change in the activity of the sun. So the picture is actually quite complicated here. So what they have here is kind of an average picture.
What's the assumption in the extrapolation from Jupiter?
What's
the assumption in extrapolation? You're saying it's extrapolated.
Right, it's extrapolated in the sense that we know that the solar wind is accelerating not immediately in the solar corona. It accelerates even up to the Earth radius, the radius of the Earth orbit, 1 AU. So then it's ballistic, you don't need to extrapolate. But if you want to talk about something closer to that, you actually need to do that. Because if you're closer to the sun, like Venus orbit, you have to adjust the 20% or so. Right. On the bigger scale, here's what we have. That's the bubble called heliosphere. The sun is over here. The wind is supersonic. It propagates roughly at the speed of 700 kilometers per second because mostly it's the fast wind. It propagates supersonically, which means it doesn't know what's in front, so it just goes ballistically. However, this system is located in the interstellar medium, so sooner or later, you actually have a situation when this wind is starting interacting with the ambient medium. It's unavoidable, basically. And since the wind is supersonic, you should expect that this transition from wind knowing nothing about the outer regions to the wind knowing that, well, it's actually there's something over there, that transition is going to be a shock. All supersonic flows go into subsonic regimes through shock. And the shock is called termination shock. Roughly, it's located between 80 EU and 180 EU, long distance away. Why it's asymmetric? For a very simple reason. The solar system is moving through the ambient gas, through the interstellar medium. And it moves not that fast. It's not really moving at a speed the sun is going around the center of the galaxy. Because the gas is actually moving in the same direction. So the relative speed is only 23 kilometers per second. But yet, it is enough to create a ball shock. So the unperturbed ISM over here, then we have a weak shock over here, and the shocked region, shocked gas, draping around the heliosphere. And this place where the solar wind plasma and the shocked interstellar medium plasma start to interact, and there's region, there's this surface where they interact, and the surface basically separates one plasma from another. They are not really mixing that much, and that's called heliopods. Then, of course, you have a long tail, which is not shown here, but actually people looked into that, and this is a very simple picture here. This is simulation from 20 years ago or so, two-dimensional ones. Here's what we have now. That's the same thing, but on a much, much larger scale. So we still have the sun here, this termination shock, and then we have lots of ripples and what is called a heliotail. The whole size of it is about 10,000 AU. What's shown here is the density, with a very peculiar contours for the colors, actually, to emphasize those ripples. What those ripples are. These are Kelvin-Helmholtz instability. It occurs because plasma that's moving here along and the plasma that's going on this side here along this interface, they move at different speeds. There's no reason they go together. And since they move at different speeds, there is shear of the velocity, and that creates Kelvin-Helmholtz instability. And those things are real. They appear basically in all simulations we have. And they're dynamical. So a typical time scale for this block to turn over is tens of years.
Is this calculation also incorporating the solar cycle? I mean, is there any 22?
Excellent question. Those ripples, these are sound waves produced by the variable solar wind with an 11-year cycle. So as the solar wind is changing in speed slightly with the 11-year cycle, the shock works like a piston. So it expands and compresses and expands again. So it's producing the sound waves that propagate further outside of the heliosphere into the shocked interstellar medium. They cannot penetrate beyond the bow shock, which is here. So yes, everything is dynamical here. Fast solar wind, is there, 11-year cycle, everything. All kinds of things are there. And then the question arises, is it the right picture? Can we actually verify this picture? And the answer is no. Or practically no. We have one way of verifying it by launching the spacecraft from here. And these are two Voyagers. Voyager 1 went this way, Voyager 2 went that way. Voyager 1 is located about 150 AU. It's somewhere over here, outside of the helipause. Voyager 2 is a little bit closer, but also probably as outside of the heliosphere, but we know that for sure because plasma instrument there is gone. Most of the data we know, we have about this region is from Voyager 1. It works perfectly well. Right, and what's next? Yeah, please go ahead.
So I'm thinking of like a similar picture where like the Earth's magnetosphere is kind of deformed itself by the solar wind, and you kind of get these tails, and then it's reconnection driven at the kind of back.
Yep.
Is that like how important is the magnetic field in the structure of this helio tail, even though you're much further out? Is it a similar sort of magnetically driven process, or is it?
Yes and no.
It's just Kelvin Helmholtz.
Yes and no. We do have Kelvin-Helmholtz instability here. We should have reconnection over there.
Yeah.
And the very fact that it actually squeezed means that there is less pressure support. So it's squeezed by the external pressure. So the internal pressure support is gone. Maybe gone for various reasons, including degradation of the magnetic field, but that's not the only thing. There are also pickup ions, which are the side product of what I'm going to talk about. So we're basically on the way along, there is mass loading to this flow.
Mm-hmm.
So it slows down and mixes with not with the ambient, well, you can call it mixing with the ambient medium because those pickup ions actually occur and are most important at the helipause.
Mm-hmm.
So right, we have pickup ions basically collisional effects, very peculiar collisional effects, and there are also collisionless like dissipation of the magnetic field. So all things are there, and that's all hopefully included in the picture. But then there's a question: can we trust that this tail is going to be that long? What if this interstellar medium is turbulent? Then turbulent motion, shear motion should destroy this. Maybe not going to destroy entirely. Maybe it's going to bend. Those motions are going to bend this, produce some turbulization or diffusion type things over here, and this tail is not going to be that long. Maybe not. We don't know. We don't know anything about those Kelvin-Helmholtz vortices, whether they're there or maybe they're suppressed. Maybe the magnetic field, the way we know about it, is not the real thing. So we actually would like to know whether this picture is right.
Chuck, just a quick question.
Yes.
So you're showing the density here, and the reason they're compressed is because of the shock.
Which one?
I mean, the bright, all these bright things. Why?
Bright things is a very peculiar color coding here to emphasize that. So yes, it's a little bit of compression. That's right. So you have this vortex and it goes around, and effectively it increases the density.
And how?
But it's not in reality. It's not as dramatic as shown here.
Okay. And how high density it is compared to the environment? Like, is it 10 times more dense?
No. Percent.
Oh, only percent.
Percent, 10%. 10% is a good approximation here. Not a factor of 2. Sometimes it's a factor of 2, but only in very specific regions. Now I'm gonna go back 25 years ago. And I wanna suggest you to go back 25 years ago, at least mentally. We don't have time machines yet. And think about this. Think about observations of comets. Here's a typical comet. And what's a comet? It's a snowball that goes along the highly elliptical orbit, gets close to the sun at some point, and then there is sublimation because of the heat, there is dust tail, there is gas tail. The temperature of this system is very small. It's basically as cold as space, we can say. It's catchy words. 20 Kelvin, 30 Kelvin, 100 Kelvin maybe. Not much. Would you dare to take a satellite, X-ray observatory, and ask the team to look for X-rays from a comet if it's 20 Kelvin? No, and lots of proposals, not lots, a couple of proposals, several proposals actually, not a couple, were declined because of that. But at some point, this great people actually decided to put Rosat, to orient Rosat and observe a comet. And here's the first ever X-ray image of a comet. By itself, it's ridiculous. A 20 Kelvin gas cannot produce X-rays, no matter what. You need millions of degrees, at least. So one need to make a theory for that. One need to explain this observation, because it's really bright. It's not just 1 or 2 photons, it's a lot of photons. Various theories were proposed, but what you should take into account is the nucleus is here. The sun is over there, so this crescent is pointing toward the sun, so it's actually in front. Looks like a shock. So there's been several theories or ideas, I should say, have been proposed which involve a shock. So maybe we have a shock here, and the shock acceleration creates a power low energetic electrons, which then emit X-rays. There's been another theory saying, okay, maybe shock is not forming because, well, it depends on conditions, because you have mass loading, so conditions are a little bit tricky here, but we definitely have an outflow from the comet, plasma outflow from the comet into the solar wind, and we'll have the solar wind flow. So those flow, meet, interact, form an isotopic distribution function. Plasma physicists love it. Therefore, you have instabilities, and in particular, there is so-called low hybrid waves instability, where the ions are not magnetized, electrons are magnetized, and you create those waves, and they immediately transfer all the or much of the energy from the ions to the electrons, and bingo, we have X-rays. Would be nice, right? We can try to look at other comets. Maybe that one is a peculiar one. This is not a comet, optical, coma, tail, UV, some blob here, so probably it's scattering of UV light from the sun. X-rays, same thing. Definitely, it's a ubiquitous thing.
What happens along the orbit as the comet gets closer to the sun?
What happens to what?
Do they vary in the?
It does. Yes, it does. There is variability, but not much.
This curved front, it always points towards the sun.
And the front always points towards the sun. Right. And what do you expect from shock theories? What do you expect from those plasma theories? A continuum of electrons from lower energies to the higher energies, no special features. And then take a spectrum, That's not shock. That's not continuum. These are lines. How can you make lines there where everything is ionized? Well, there's a way. That's called charge exchange. And I'll talk about this in just a moment, next slide. But people realize that pretty quickly, within a year or so. And here is a simulation of cometary X-rays, assuming this charge exchange process. Here's the real image. Here is the simulation, morphology, intensity. They'll do all real well. What I like is this paper. They actually reproduce the spectrum in the lab. So those things are indeed real. You can actually measure it right there on your table. So what's the charge exchange process? The charge exchange process is a process of transfer of electron from one species to another species. So we assume that we have neutral hydrogen. Neutral hydrogen is ubiquitous. So if you need neutrals, neutral hydrogen is there. There is a little bit of helium as well. So for correctness, you actually have to include helium as well. And then assume that you have another species being a highly ionized ion. What I mean highly ionized. Oxygen 8+. That's bare nucleus, no electrons. All the electrons have been ionized from it. Oxygen 7+. It's helium-like oxygen. Nucleus and just one electron. So lots of orbitals, so to say, speaking chemically, are empty there. So the charge is huge. And the potential here is deep. So as you go up here, you have lots and lots of energy levels down there. The density of the energy levels there is large. The energy density levels here is small, but it doesn't matter. This neutral is sitting in the ground state anyway. And imagine you have this highly ionized ion, and the neutral is passing by. They pass by each other, get closer at a certain point, and you're gonna have a transfer of electron under the barrier, quantum tunneling. It may happen without change of energy of the electron, because the electron here has certain energy, which is the ground state. It can almost always find an energy level in the new ion if it goes there. Once this one transfers electron from here to there, this one becomes ionized, so it's singly ionized helium or just a bare proton. That's called pickup ion. Once it becomes ionized, it becomes pickup ion. It stays with the wind because neutrals can go freely through the heliosphere because they are unimpeded by the magnetic field. Once this particle has a charge, it's going to be frozen to the plasma, so it moves with the plasma now. It provides mass loading. There were nothing here, and then you get an extra proton. If you have many of those protons that are kicked up, the density increases. That's how you have mass loading at large distances. And this is a collisional process, but very peculiar collisional process. What happens here? The electron is transferred over here and finds itself in a highly excited state. And it's going to cascade down to the ground state, emitting all possible photons with certain probabilities, including X-ray photons. That's how we get X-rays from there. Why it's called resonant? Because the energy is the same. If you remember, the transition probability in quantum mechanics, the matrix element, has 1 over the difference of the energies between the initial and the final state. Now here the energies are roughly the same. So what you have in the denominator is just small line width essentially. Right? So the matrix element is very large. The denominator is small, the matrix element is large. The cross-section, which is the square of the matrix element, is even larger. So cross-sections go up to 10⁻⁵ or even a few times 10⁻⁵. nearly 10 orders of magnitude larger than the Thomson cross section. So it's a very efficient process. Right, where do we get those ions? In the corona. Corona starts cold, but the temperature of the corona goes up really, really quickly as a function of distance from the sun, from the sun's surface. And as the parcel of the gas moves along that line, it remains in ionization equilibrium. So as the temperature is increasing, you have more and more ionization, which is dictated by the temperature. And finally, the temperature flattens out at a couple of millions of degrees. Ionization, equilibrium, whatever it was, stays there, and then the wind dilutes. All the electrons and the ions go away from each other, the density goes down, recombination is suppressed because density is low, and we have freeze out of this coronal composition of the ions. One can measure that, and all goes well. That's a real measurement. Silicon 10 plus, 9 plus, 8 plus, so on. Iron 13 plus, 12 plus, 11 plus, so on. All works well. Can we observe anywhere else besides comets? Yes, coronal mass ejections. Comets are nice because what you have there is a really unlimited source of neutrals. So the comets are going to be the brightest in X-rays and in charge X-rays, charge exchange X-rays. But Earth is also a source of neutrals. We have atmosphere, and even though it's not that much that goes up there, exponentially small in fact. But if you have a coronal mass ejection, it's just blob of gas that's detached from the sun during the solar flare and propagating outward. Sometimes it can meet the heliosphere, and it can exert some pressure on it, so it moves this front edge a little bit inward. But the density is exponential, so as you press it inwards, you increase the neutral density large significantly. And you have this, what's called geocorona. So you can take a satellite and just observe something, whatever you want to observe. Maybe you observe some background. If you observe it during the quiet time, and then you observe it during this interaction with the CME, and take the difference of the spectrum, here's what you get. All those lines, and they're nicely seen.
H1 clouds also, is that like similar?
Huh?
H1 clouds?
H1 clouds should do the same, right? If we talk about galaxy, right? We have lots of X-rays from the solar system bodies. Not all of them are charge exchange though. That's definitely charge exchange because you can see it from the crescent shape. That's definitely true because I just talked about that. What about moon? There are no neutrals there, practically nothing. Well, that's from the surface. Essentially, this fluorescence. You see the fluorescence in the X-rays. Same as here. Not sure about the Saturn rings. Jupiter, well, that's kind of strange, right? We have polar caps here. It has to do something with the open field lines. Yes, it is aurora. In particular, Io produces lots of sulfur ions, which precipitate and produce aurora here, and you see the aurora on the Earth as well. So we do have that. How about Mars? I'm not sure if you see that well. Of course, you see the main thing, and of course, this is fluorescence. But we have single photons here and there. And it looks like they're distributed randomly. If we dim the lights, we can probably see it, but at the moment, you can just trust me. If you beam them as a function of distance, so take annuli bends and bend the number of photons, the number of photons decreases with the distance. These are charge exchange because Mars, it has feeble atmosphere, but nevertheless, there is this exosphere and neutrals are there, and you can see those charge exchange photons from there, that interaction as well. We actually modeled that a long time ago. Now to the modeling. So for the modeling, we need several things. Before that, I'm not going to talk about this big simulation. I'm gonna focus myself on this region of about 1,000 AU cubed or squared in this case. But that doesn't change anything in terms of science, in terms of methodology. First thing we need to do is we need to make a heliospheric model. They're available. And before jumping into the whole detail here, let me just say, well, this project is a pilot project. It's been done as a post-processing for the heliospheric simulations. These are tens, if not hundreds of millions of CPU hours. And then we just use snapshots we obtained from them to make the time-dependent model that's going to be used for the reconstruction of X-rays. So ideally, we should get X-rays right there as a diagnostic tool of the data that you produce with the simulations. But here's what we've done, because we don't have it yet. We need the model to determine how gas is moving. And here's the model. It's a small one. Its density shown here, contours, the sun. This is the shock. That's just the change of the color. And there is some draping toward the heliosphere. Next, we need to calculate the evolution of species. We have many species there. We have lots of ions, as you figured. So for each species, for each ion X with a charge Q, we have to see how much we're left, how many ions are left due to the charge exchange from state Q to Q minus 1, and how many came to this equation from charge exchange of Q plus 1. So it's a Q plus 1 transition to Q. So this is the sink, that's the source. And we have N ions, so we have N coupled equations here. Really easy to solve. For this particular project, we were interested in energy range of X-rays between 0.1 and 1 keV. So we basically chose to consider all relevant charged species, practically all. Maybe some really dim ones, I mean, which produce real dim X-ray lines below 1% or so are emitted, but most of them are there, including helium-2, which is not actually producing a line, which doesn't have a line above 0.1 keV. It has a line at 70 eV. But it's so strong because there's lots of helium that actually blends into the spectral region that we consider here. Next, we need to calculate the volumetric rate of production of X-rays. You don't need to do anything here because this is it. You have an ion with a charge Q plus 1. It picks up the electron, becomes ion with charge Q. This ion with charge Q is in the excited state. So it is this ion that produces the cascade of X-rays, cascade of photons, which include X-rays. So the rate of production of X-rays is this, 1:1.
Can I ask a question?
Yes, please.
So is the kind of de-excitation time scale then much smaller than?
Absolutely,
Yeah.
negligible.
Okay.
So pretty pictures. This is O8 line. O8 line is produced by O7 plus ion, being an excited state and then goes down. So I will be using both the ion species nomenclature and the line nomenclature. And they're different by one. Because neutral is producing, like neutral oxygen is producing O1. Single ionized is producing O2 line and so on. So O7 plus is producing O8. So that's how production rate, if you like, intensity, crudely, looks like from the outside and then cross section. Yes.
So you had mentioned at the start that the reason that this is, a very common occurrence is because you have some similarities in the energy levels between the initial and the final state.
Mhm.
And at first I thought that was a peculiarity of that example that you mentioned with neutral hydrogen and then, at O7, but it sounds like this happens actually much more often with many ion species.
Yeah.
Do you understand why all of these energy levels are just so similar across the initial?
You don't need to have them exactly the same, right? And if those energy levels are not exactly the same, then there is some delta E and that reduces the cross section. But since they're in the same ballpark, right? Essentially, we're not talking about factor of 2, we're talking about percent. So it's tens of percent maybe energy difference if realistically. I actually don't have them at the top of my head, but we can calculate.
Especially velocity.
And there is, yes, thank you, Rashid. And there is dispersion velocity here as well, Doppler shift.
So you also need a source of neutrals, so to start this whole thing, so.
Yes.
to model that, is there another equation you have to add for the
Yeah,
neutral evolution species?
right.
Where are they coming from?
Right. Thanks for asking. I actually forgot to tell about this. Where do we get neutrals in the heliosphere? Neutrals are from the interstellar medium. We have about 0.2 particles per cubic centimeter of neutrals. And neutrals are not impeded by the magnetic field. So they can penetrate freely. They don't know about magnetosphere effectively. They penetrate deep inside the magnetosphere. And it's more or less uniform background up to roughly 5 AU, where UV radiation from the sun is starting to ionize some of them. And as you get closer to the sun, the ionization actually becomes stronger. So you have a depletion of neutrals near the sun. But beyond a few AU, and for the outer heliosphere, that's certainly true. So it's a question of what's happening right next to the sun. So for the entire magnetosphere, entire heliosphere, you can just say it's neutral background of 0.2 particles per cubic centimeter. But yes, you do need neutrals. So if your interstellar medium is fully ionized, you will not get that.
So there are more neutrals than can be charge exchanged across the whole heliosphere. In other words, the density of neutrals doesn't really change across.
Right, there are lots of neutrals. Because now, in one of the previous slides, I'm not going to go back, but the amount of ions, highly stripped ions here is like 0.1%. It's fairly small. So charge exchange is mostly important for hydrogen and helium from the sun than for the ions. Yeah, yes, there you should actually take care of the neutrals and consider them correctly. So the model that I showed, it's actually an MHD model with the particle component, which calculates neutrals separately and allows it to correctly, as far as we know, correctly represent the interaction. And that those pickup ions, those interactions with the neutrals and degradation of the neutrals there toward the heliotail is actually seen. So it's a real thing.
This might be a related question. When you have ionization and mass loading into the magnetic field, does that back react on the field?
It does. You have more mass, right? You have mass coming out of nowhere, so your plasma is getting denser and denser.
Does it strongly affect the magnetic field?
It doesn't affect the magnetic field, but it does affect the dynamics. It slows down the thing.
And in this simulations, that's not.
Yeah, it's all included.
It's included.
Yeah.
But do you resolve here shock waves or not? Because very important thing for.
Shock wave, of course, yeah.
Because it's necessary to resolve, and then the shock wave also ionizes neutron gas and so on.
Yeah.
Because charged protons are stuck there.
Right, here's the shock, it's resolved. There is actually a hydrogen wall over here because of that interaction. And of course, it's resolved here as well. You can see where the hydrogen wall is supposed to be, there is over density. So it's all there. I mean, there are many details which I am actually skipping here, but of course they're there, they're real and they're important.
And hydrogen density is not uniform.
It's not. Hydrogen density is not uniform. There is another thing. There is a helium tail over here as well, which you have to include because helium is heavier and therefore it's bound by the gravity of the sun stronger. There are details there as well. There are lots of interesting stuff. Right. Where were we?
And you will not tell us about anomalous cosmic rays from that region?
No. I am completely neither. That's another very interesting story, but I cannot put everything in a single talk. That's right. So I'm talking only about those cold X-rays, not so-called hot X-rays which come from hot regions. So here's how a heliosphere looks, or would look to the little green man on Alpha Centauri, if they want to observe us. And you see, there is an interesting effect that higher ionization species are concentrated near the sun, lower ionization species are actually distributed more smoothly. Why is that? Well, because of those interactions. We can quantify it by so-called collisional depth. Optical depth is known, right? You have optical depth of 1 when a photon has 100% chance of interacting and getting scattered. Same thing is here. A collisional depth is 1 if an ion has 100% chance of experiencing a charge exchange process and being switched from Q charge state to Q minus 1 charge state. That's optical collisional depth of 1, collisional depth of 2, 3, 4. So roughly you can say this distance is the mean free path due to charge exchange collisions, and it's roughly 150 to 100 AU. So whatever you put here, oxygen 8 plus, for example, becomes oxygen 7 plus here, oxygen 6, oxygen 5 plus. This collisional thickness effect is best seen in the neon, because neon has lots of X-ray lines. That's why we consider it, although they're quite dim, but nevertheless. Here's the distribution of 8 plus. It's mostly near the sun. 9 plus, 8 plus, 7 plus. Now you see that it's fairly uniform, and you have lots of neon 7 plus created from the charge exchange, in particular here, because the density here is of neutrons is larger, the density of the solar wind is larger. Okay, next, we're start seeing depletion of neon 6 plus over there. Why? Because we don't have that many of neon 6 pluses emanating from the sun. Its ionization energy is smaller than the 2 million degrees temperature near the sun. Here we don't have neon 5 plus at all, so it's empty cavity, and then you start seeing stuff, and even more so for neon 4 plus. Right. Next, we want to compare what we've got with observations. So we want to calculate spectra. Calculation of spectra is straightforward as long as you know cascade probabilities, and this is a big unknown. There is a lot of guesswork here. In the spectral line positions, we have catalogs, so we can use that. Here's what we have for XMM resolution. Chandra resolution is too broad to see nice features. Same graph here and here. That's just normal counts. That's the log of the count, not count, intensity. So it's photons per square centimeter per second per steradian. You take your telescope, pointed, and that's the background that you will see. Oxygen stands out here, and the bright lines are shown here by the species. So that's oxygen 6+, so it's O7, this is O8 line from O7+, carbon 5, two of them, and there's a mixture of magnesium and carbon 5. Yes.
Be pointing XMM to be able to resolve this, or you're trying to do like anisotropic measurements to see how this is changing, like on one end of the solar system, like in the direction of the dipole and then the other side?
I'm coming to that. Thanks for the question. You will see that in a moment. So these are the morphology of the dormant lines. I'm not going to spend much time here. Just look how they look from the outside. And now to your question, calculation of the X-rays dimension. One can do that for each line. There's no problem with that. What's shown here is the oxygen. Of course, we have really simple two-dimensional model. So what we can get outside of dipole. But dipole is significant. It's 50%. That's the difference between the nose and tail. 0.02 over 0.04. So it's significant. 40% maybe. So yeah, just by rotating the telescope around and having nice spectral resolution, so focusing on a specific line, you can actually try to map it and figure out which way we're going. And that should be possible, even with existing data. And we do have data available.
Sorry, the
yes.
continuum on the plot? How much was the continuum, the metagalactic background on this plot?
Way more. That's the problem. But you know what the signal to look for, right? You know that you're looking for the dipole signal with maximum here, minimum there. So this galactic background, it's there, but you can try to filter it out. We worked with Rosat data. Unfortunately, we don't have access or even ability to do Rosita. I don't know if it's going to be operational again, but I really hope things will change. But
there's a lot of data, and in Rosita, the main contribution to the background, which is quasi-isotropic, is the Velo emission of the hot gas in our
that's great.
Much more than metagalactic flux.
Oh, that is great. So if somebody can actually help me with this, I'll be real happy to do something useful using the available data. What I can tell is from what I know, the data that I looked at, those dim spots here along the galactic plane, that's where you have most of the background filtered out. It's obscured. So that's why the flux is minimum. Over here, the heliospheric emission is about 40%. And it's not only our result, other people actually estimated to roughly the same, 40–50%. So half of the emission goes from the heliosphere, and it's a broad Rosat. Rosat is not really any, it has a really bad spectral resolution. So everything is dumped in there. But even over there, you can tell that. If you have better spectral resolution, you can probably do better.
There is maybe you know about the Denmark common rocket flight, student rocket flight, where he has colorimeter, and therefore they found all the lines. And lines are enormous amount of time higher than the background. These lines which originate from the charge exchange, it's beautiful.
We need to talk about this.
Okay, but I'm just telling to everybody that there are experimental data from student flights. Just this was a diploma works of students, and rocket flight, which was 7 or 10 minutes. And during that 10 minutes, sky is so bright in these lines about which we heard now from our speaker, that they are much higher than the background, and this student experiment is much better than Rosat and even the Rosita, because there is no background. You see only narrow lines.
Yes. Yeah. Unfortunately, I didn't put another slide like this one, because that's XMM resolution and lots of things is blurred. But imagine you make this line, it's 10 times thinner. this whole emission is gonna be peaking like crazy.
Now there is a new spacecraft, Japanese spacecraft, which has calorimeter with a resolution of the order of 1 electron volt, maybe 5 electron volts. And therefore, instead of hundreds of electron volts of zeta or and so on, you see these huge lines now.
Fantastic.
I think that we should wait for several months or a year.
Fantastic.
And you will get enormous information by the new X-ray data.
Wonderful, thank you. So this is a little hanging fruit. People jump. Let's do it. Let's actually do the. Let's put the. Let's put this charge exchange thing into the available codes. Right. It's easy. It's a matter of, I don't know, a month maybe. And then we can get that on the fly. You can get all this data on the fly. And a couple of words about other stellar systems. We don't know much about them, although there are some observations which tell us about the mass loss rate and stuff like that. Here are just the 3 images of stars with the bow shock. Here for the Cassiopeia, for the Orion stars. And this is a beautiful one. Its tail is about, 10 light years or so. And a bow shock here, and some emission over there. This is from mirror, and it is not X-rays though. This is ultraviolet. One can actually try to study those objects. I didn't know about this Japanese observatory. I have to look it up. I was focused on the next generation of telescope, the advanced telescope for high-energy astrophysics, which is Athena in short. And that's going to be really beautiful, especially for Alpha Centauri and Epsilon Eridani, which has the mass loss rate of about 30 compared to the sun. Sun itself at 5 kiloparsec, at 5 parsec would not be that well observable. You can probably get some counts, but not that much. And I'm gonna stop basically here because this is, again, another demonstration that this is a low-hanging fruit. People have data, we will have more data, and it's a question of just making those simulations, making predictions, and get that nice, nice project done. Overall, very important statement. Charge exchange cosmic, charge exchange solar X-rays, solar wind charge exchange X-rays is really underestimated process in a way of studying other systems, because it gives you a unique way of telling decomposition, temperature, evolution of the corona, density, evolution of the density, and morphology, and also the environment, the interstellar medium, turbulence in it, and so on and so forth. And of course, you can do other things like space weather and sun-earth connection if you like as well. That's it.
Question for me?
What about the CMEs from other stars? Because we know they're like super flares. They're probably like super CMEs. Is it possible to detect?
The CME itself is hard because the density contrast there is not that strong. Probably you can see CME in a form of variation of the flux at the outer heliosphere when it goes through the termination shock and pushes on the heliopods. But it's going to be quite weak over there, honestly. I don't know. Again, that depends on the model, depends on the mass loss rate and stuff like that.
The contribution from like cosmic rays would be like subdominant to what you mentioned, or?
There's a lines.
Yes.
So you can have great spectral resolution. Contribution from cosmic rays is nothing.
Again, due to dispersion of velocities, they go in different directions.
Yep. Thank you.
It's a great subject now, and there will be several new proposals much better than Athena. There will be LISM, this new American. It will be white paper, I think, will appear on AstroPH in several weeks. And this is a joint project of CFA, Goddard. There is competition now for middle class missions. And it is again X-ray colorimeters. Therefore, you can measure
Microcalorimeters.
Yes, there will be microcalorimeters. You're completely right, but we already are speaking.
Okay, well,
Cryogenic calorimeters in the simple research. And
obviously, yeah.
it's the same. And it will be really great. I have with me prepared to show the new picture based on the data of Rosita, how people will see this background. I have no right to emphasize, it's still even not submitted, but there are beautiful picture and heliosphere and all the things, charge exchange, business, people worked enormously well, based on the data from this outer Earth atmosphere. Because there are many geophysical spacecraft, which also measuring the same, and reactions are completely the same. They only include much more elements. You are speaking mainly about hydrogen and helium, but there are beautiful resonances when you have different ions of this chemical abundance of the universe. You will get even much more rich picture. This is great science, new great science now, because there will be a lot of new experimental data very soon.
So I wonder what's the best target for other stars?
The best
how
target.
many of that will be observable, you think? And also, is there any difference between main sequence stars and like other types of massive stars? Will it be better, or red giants? Will that difference be anything interesting?
I didn't look into that. Obviously, the larger the mass loss rate, the stronger the signal. It's just a number.
The mass loss rate will give you neutral.
But yes, but you need to have neutrals. And that's a big question. So you need environment. And those OB stars probably ionize everything around. So I'm not that optimistic about them. People usually in this business, not so many of them that I know at least, they are actually looking at dwarfs mostly for the reason precisely because the environment is not as much affected by the ionizing radiation. But you do need neutrals. That's a very important thing.
Rosita sees now hundreds of the brown dwarfs due to the X-ray emission. And I'm sure that a significant part of this emission will be again in such lines. Brown dwarfs, they have, there are many brown dwarfs which
why they are emitting X-rays?
They emitting X-rays. Main ideas are the following: that they do not have good radiative transfer because it's neutral. Very deeply, the atmosphere is neutral. But if you have convection, you understand me, and this only way to take very low luminosity, but convection carries much more energy than radiative transfer. Therefore, we often see X-rays more bright than the infrared emission, just due to the convective process. And then you have immediately, you go to chromosphere, corona, and so on. And this is beautiful thing, new and irradiated will. I think that there will be thousands of brown dwarfs discovered by Rosita. Now we have only on half of the sky 196 brown dwarfs. Additional thing is there is great science. You know that you are burning initial plasma, and in initial plasma there is a lithium created during first 3 minutes. Beryllium is created, and then beryllium provides you transfers to the lithium. And this lithium has a rather low temperature of ignition, and everybody knows that there are no nuclear reactions in the brown dwarfs, but because lithium is burning and it adds some short stage brown dwarfs are becoming much more bright. Due to the lithium very rapid, you understand this, then lithium is burning, and this is primordial lithium.
Yeah.
And then you are getting rather higher luminosity and so on. And again, the convective atmosphere and again X-rays.
But like you mentioned, I mean, you could have like a star near some molecular cloud, like some transient phenomena where you could.
Yeah, you can. Yeah, absolutely. If you have, no, nice thing would be a star going into the cloud. Right.
Transient.
A transient. Yeah.
So you computed these maps for the different ions, right?
Mhm.
And so is the idea that then you make the intensity map and see a different dipole for each of the lines? So-
Yes, we actually checked that. It doesn't look that different, but it does look different, especially if you consider this degradation of the species down to the helio tail. Yes, there is appearance of the lines which are not existent or very weak on the nose, but they are kind of dominant in the tail. Again, it's a question of whether you can measure them because they are not that bright as those oxygen lines. But yeah, if you can measure that's right. Suppose I have a wishful thinking that we can observe all the lines we want. Then it's going to be tomography of the heliosphere. Because different lines give you different positions.
To try to see if there is this long tail. And
Yeah,
stuff like
you see the long tail, and you see each fraction of the tail is a function of distance, and so on. So it would be nice if we're able to measure that. But it's going to be tricky, I guess. But no, probably not. According to what you say, probably not as tricky if you have a really good spectral resolution. Then you just focus on a different particular line.
This is very important. And second, there is well-known way to see the inhomogeneities in our solar system in the gas, interplanetary gas system.
Yeah.
It is the resonance scattering of Lyman alpha and helium resonant lines 584 and
Right,
so on.
right.
They are scattered on the neutral component.
Right.
It has different velocities and ionized, and then you can put the.
So you have absorption and you have wings,
Yes,
which
this
is the
a
emission.
pool where the
Right.
gases, hydrogen is going so around sun due to the pressure from sun, and helium is concentrated because it's here
Yeah.
heavy behind the sun from
Right,
us.
right. I think actually
Well,
Woods did those observations, I believe, Woods or somebody else. I've seen something like that.
Different countries.
Yeah, there are people, there are people who are actually doing that.
These are all, these 20 years old.
Yeah.
Let's thank Misha again.